Let's get started. First of all, thanks everyone for staying here. I know it's been a long couple of days, but we really appreciate you guys coming, staying for the whole 2 days and staying until the end. Hopefully this can be a little more like a lighthearted conversation. We're gonna have space for questions, so if you want to ask anyone, if you guys want to be part of the conversation, we will have some time for that. I think we heard from most people here. I think maybe Zoltan was the only person who somehow didn't give a talk.
That's true.
Maybe we can start with a quick round of introductions, starting with you. Maybe just introduce yourself, and if you could maybe spend 1 minute just saying how you're involved in this whole hardware acceleration industry for data management.
Sure. Hi. So my name is Zoltan. I work for IBM Research. And I'm a software engineer working on GPU integration to Velox. So obviously this became for us also a good future outlook, right? To get hardware accelerated into Velox, because we see it also as a very good cost performance play, right? Not so much looking at the AI pipelines yet, but that's coming. But traditional SQL, right, is still a huge business. People still run traditional SQL. I know that hasn't been the focus of the last 2 days, right? But lots of traditional SQL still running, migrating to Velox, and I'm super excited about what hardware acceleration will bring to Velox. Yeah.
Thanks, Zoltan. Felipe, do you want to go next?
Yeah, so I'm Felipe. I'm an architect at Voltron Data. I've been working on distributed SQL execution engines on NVIDIA GPUs for about 10 years. Just always been, wanting to work using CUDA, which is really hard to use, and allowing you to kind of stay ahead of the pack when it comes to performance. So I don't know. I've always liked working on GPU accelerated problems because it's just a lot more challenging than just working on the CPU. Yeah, that's me.
Definitely very challenging. Rajan?
Sure, thank you. This is Rajan Goel. I just finished my talk. I'm CEO and co-founder at DataPelago, but engineer by heart. So my previous life, I've spent a lot of time on hardware software code design, building domain-specific processors, MIPS and ARM-based processor for security, for data movement, and so on. But it's a much more fascinating world, I would say, the world of data, and it's becoming more and more exciting with the Gen AI and unstructured multimodal data. But excited to be here, and thank you for the opportunity here, Pedro and team.
Yeah, definitely. Thanks for joining the panel. Greg?
I'm Greg Kimball from NVIDIA, leading the UDF effort. And earlier I heard from Zoltan that he'd been trying to use Thrust and Cub to do some query processing. And that's kind of what UDF does under the hood, actually, right? I mean,
yes, Felipe said it's really hard when you go down to CUDA and then Cub and then Thrust and then whatever in between, right?
And then you go from Thrust to UDF, and that's but you can kind of plug into the stack wherever you like, depending on how much patience you have. But we want UDF to be a good for the low patience consumer who just wants to work in C++ and get things done. So, anyways, really excited for the discussion.
Thanks, Greg. I think everyone knows Ori, but Ori, do you want to introduce yourself?
Right. Okay. So I'm Ori from Velox. I've done many years of any kind of database performance-related stuff from the times when SQL was new. And then for the longest time, I was working on a system called OpenLink Virtuoso, which was kind of my baby. And that was anything from SQL Federation to XML to RDF, semantic web, linked data, if anybody ever heard of that. And then since the company was going for that to the exclusion of better pursuits, then I was at Google for a while and then joined Meta and studied Velox. And a relative newcomer to GPUs, I've done all kinds of performance-related stuff forever. Performance, I'm Challenger Cat, I want to go for it. Climbing trees. So GPU is kind of the new tree to climb, so I'm a relative newcomer, but I'm trying to figure out the basics from the ground up and see how we can bring something new to this game. But it's a very challenging environment. It's very cool. I like it. And we're in excellent company with tons of talent and exciting stuff to do.
Cool. Yeah, thanks, Ori. We have this internal joke that engineers are like cat because they don't like to be told what you do, things like that. So Ori is the challenger cat. He likes big challenges. That's the context. Yeah, thank you guys for coming. So we put together this panel. We tried to make this as mixed as we could, having people sort of from different perspectives. We have hardware vendors. We have people building products on top of this hardware architecture. We have people from research community. We have users like Ori and me. So I think it's nice that we get slightly different perspectives on this whole space. I would like to start on a little bit more from the adoption perspective, right? So hardware accelerators, GPUs, ASIC accelerators of all sorts, FPGAs, they have been together for a while, and people have been kind of proposing and trying ways to use them in data management for at least a decade, maybe a couple of decades. So I'll love you guys. Could you comment on where you guys think you are from your perspectives on this kind of adoption curve?
Yeah, may I? Yeah. You know, it's funny. You could look at papers published in the last 15 years, like up to I would say 2010, 2012. There were lots of papers about accelerating databases and GPUs. But basically, if you read all these papers, their conclusion was, oh, we're hitting the PCI limit, or we're hitting the disk limit, or we're hitting some network limit, right? So everyone was hitting kind of hardware limits. And then they said, okay, we can't do anything about it. That's hardware. We're going to wait for the hardware to catch up. And I really think, so from an adoption perspective, I think we're there where the hardware did catch up, mostly thanks to AI ML, right? So we're just driving on the back wave of AI ML innovation, which we can reuse for data. But also we're kind of late in a sense that lots of research have been done in the past that now we can use the same research and get much better results. So we should revisit what's been published, what's out there already to gain insight into why does that work today, right?
The engine's also changed a little. So at the very beginning, a GPU was seen as sort of this co-processor that you would pick a small amount of your workload and push it out to it, which meant you had to go over PCIe every time you wanted to do anything on the GPU. And then we started saying, well, now we're going to build pipelines, and we could do these 5 to 10 steps on the GPU. And now we're talking about accelerator native, where you don't leave the accelerator's memory unless you're spilling, right? So now I think that, in addition to all these things getting faster, we're also being smarter about how we build these systems.
I mean, it helps that the memory grew from 8 gigabytes?
2.
Okay, so right, or 2 gigabytes, right? Now we're up to, almost 200-ish, kind of, right?
So you're saying that you're moving from a place where you had accelerators for part of the engine, where now the engine is actually natively written for the accelerator. Interesting. Any comments?
Sure. Few comments. I think in order to make this successful, the problem has to be meaningful, which it is now. I would say it is much more problem to people are hurting if you don't do the accelerated computing. Cost is untenable. That's one argument. So it is a problem to be solved. You cannot ignore it by just running into some roadblock. The second is, as he said, the IOs are getting up, meaning improving. If you look at the improvement of the IOs in last 4 or 5 years, they are beating the CPU performance or the compute performance. So PCI or the disk or the networking, they are much steeper curve than the compute. So we used to 10 megabit or whatever, or those kind of network links. Now we're talking about 100 gigabit or even more than that. So the IOs have already caught up. So CPU is becoming a bottleneck. And the third thing is that it is not an easy problem. I think I just want to go back to the main question somebody asked. How do you handle spillover? How do you handle hash table larger than the GPU memory? No matter what's the GPU memory, you will always be 1/10 or 1/100th the total data set size. You still have to solve algorithmically, re-express your algorithms for this target thing. That is a very hard problem. You can't just, I'm just kind of stealing the word from Jensen and NVIDIA. He says, one of the challenges you have to re-express your algorithm for this target thing, right? That is not an easy problem to solve. Hence there are multiple technical challenge to be solved, PCI bandwidth, and as Felipe was saying, how do we be smart enough not to do the domain crossing and so on and so forth. But fundamentally, economics make sense. B, the infrastructure is now much more available. GPUs are available every region, every data center, thanks to NVIDIA. The CUDA framework is much more mature, right, which for adoption of that, which was not there earlier. And most importantly, it is a time when customers are hurting. If you don't solve it, you can't just avoid it. The gap will keep growing. So the business is demanding for us to solve it. So, I mean, I think now it is up to us to solve it together as a community.
Yeah, no, I think that's a great perspective, right? So you're saying that the hardware platform has been advancing to a point where, now we have the right things. The science, it seems like we're already there. We already know how to build those systems. Then what's next? What's the next bottleneck for this?
And just maybe one more thought there. What helps a lot is that all the AI folks, they always want the latest hardware, right? So they basically, a new hardware architecture comes out, they want to move instantly. At least that's what I see, right? The AI guys I know, they always want the latest. So what happens to all the hardware that's been deployed, especially if you're looking at like 2, 3, 4 year refresh cycles, right? All the A100s out there, they don't want it for AI anymore, right? Not for the AI training, actually, right? So all that hardware is now becoming more available. You'd be hard-pressed to get Blackwell or Hopper from NVIDIA, but A100 or the inference cards, they are plenty available, right? So this helps adoption as well, right? If you don't want to run it on the latest.
That's correct.
Yeah, and just I think continue on that topic, now that we have the hardware, the right hardware platform, it's available even in public clouds, what is the next bottleneck? Like what's missing for us to move data management completely into this hard platform? Maybe Ori can comment on that.
Right, okay, so the good thing is for many years we've always said it was a next generation of GPUs that was going to be good enough. Now they're plenty good enough. Like Felipe said, A100 is fine, and they're available. The AI for us, let's say, the most expensive models don't make sense for data management cost-wise. So what we need is a mid-range GPU that's available in quantity. Of course, the scarcity is going to fix itself. There'll be more supply eventually. So that will sort itself out. The thing is functional completeness, staying within maturity, spilling, for example, staying within the accelerator domain. If you're on accelerator, you better stay there because crossing the boundary is expensive. And if this is going to be the only platform or the dominant platform in a data center, because we're procuring data centers now that are mostly GPU data centers, so if that's the only kind of computer you got, then you got to run all your work there, and this demands something from software maturity. Also, if you're going to build a data management data center as opposed to an AI data center from GPUs, then you're not going to make the investment unless the technology is sufficiently mature. However, for smaller applications, the wide availability of that stuff on public clouds is going to be good because smaller applications absolutely can be deployed on clouds whenever the software maturity is there. So like my call to this community would be, okay, let's fix the long tail problem and let's do benchmarks.
And I think maybe double-clicking on that point about workloads. I think, Zoltan, you mentioned that you and your team are doing a lot of work on just supporting more traditional SQL workloads.
Right.
I think there's this idea of sort of data consumption, right? Getting this data into dashboards. There's the idea of kind of transforming data in the warehouse, data pipelines, all the way into the whole discussion.
All boring workloads.
Yeah, I wouldn't say boring, but yeah, more like SQL analytic workloads. All the way to this discussion we had yesterday on kind of training, getting this data out of the warehouse, feeding into trainers. How do you guys see this spectrum of use cases, and what's a good target for those accelerators?
I think maybe we need a mix, right? Like Ori said, we need a mid-range GPU and build the data center with it. Maybe we need a mix. I think, it depends if you want to throw everything in one box, right? Which I don't think you can from a cost perspective also. If you want to push your training pipeline and your pre-processing pipeline together for the AI workloads, right? Then obviously for the training you want the latest hardware, which for normal data doesn't make sense, as we discussed, right? So I think you need a mix, but this mix needs to be on the, it can be in the same data center, right? But I think that's an open question, at least from my side, definitely. A GPU-only data center where you have one kind, I think that's hard, right? Because partially of the long tail and partially of the mixture of workloads that you're running.
Some of your workload.
Go for it.
Some of the workloads are going to spend very little time moving data onto the GPU and then do a ton of computation on the GPU. And in those situations, we found that the more expensive ones are quite wonderful. If you're shoveling data across, if you're moving data from slow centralized storage to the GPU, the more expensive GPUs are almost never justified because you can't get the bytes into the GPU fast enough. You'll never fill it up. You're done processing and have moved on to the next thing and you're just starved for data. And that's where the older, cheaper ones have the benefit of, while the GPU might be older, well, the network cards got a little bit better, and the SSDs got a little bit better, and then the RAM got a little bit faster. And so all that sort of helps. It's like you're catching up to the accelerator with all of the other things around it.
Yeah. I think on that topic, another point that was interesting is, I think, Zoltan, you mentioned that historically the bottleneck was that we couldn't get data in and out of the accelerator fast enough, and now those things are catching up. And yesterday we were having a discussion with, I think Victor was also partly there. We're saying that the bottleneck in a lot of cases is actually the memory throughput on the device, right? So it seems like the bottlenecks are changing. And can you
like, just to, maybe for the audience, just to put some numbers on these bandwidth numbers we're throwing around, right? On the A100, you're looking at like 2 terabytes a second device memory bandwidth, right? And per GPU, you're looking at 200 gigabit towards the network, right? If you go one up to the Hopper series, you're looking at 4.8 terabytes a second device memory and 400 gigabit on the network, right? So you see device memory bandwidth doubled roughly, network doubled roughly, right, as Felipe said. And then if you go up to Blackfly, you get like 8 terabytes a second. I'm not shilling from NVIDIA, it's just the spec I know. And you know, put it into perspective, like to PCI Express, previously you were happy if you could do like 10 gigabytes a second, right, on 100 gigabit. And now with NVLink, you can do 1.8 terabytes a second, right? So it's just you know, hellishly fast. And so but the old stuff is fast enough, right? Like cost performance, as you mentioned, it doesn't make sense to put any accelerator there if you're just waiting for I/O, like the network I/O, right? And yeah, so just numbers-wise, I think these are the numbers. And for main memory, it's like 500 gigabytes a second. So the accelerator is already, you know, 4 times, between 4 times and like, was that like 16 times faster, right?
Can I make 2 comments? So one is just to echo back what Felipe mentioned, is that at architect level, you want to have an impedance match between your compute and the I/O, right? That's the problem statement. Obviously, in the beginning, I/Os were behind and it was not helping, but now I/Os have kind of improved. So ultimately, architecture level, within a node or across distributed systems, we are talking about distributed system here, you need to have an impedance match between your I/O bandwidth, whether it's a PCI or the DRAM or the network, with the compute. And if you look at from that perspective, and if you do that math, you will zero in onto the right GPU, which is kind of sufficient for that. And luckily or fortunately, that happened to be the lower end GPUs or more available GPUs, which is the good thing to have from engineering point of view. The second point I will make is that if you look at the historical GPU's evolution itself, when they started getting used for AI world, none of them had tensor cores, right? They were just designed for graphics. So people were still figuring out a way to use graphics-defined GPUs for AI workloads and so on, right? And that time, GPUs were not efficient designed for that. But as workload became more prominent and important from NVIDIA point of view, all the modern GPUs have first-class citizen is inference or training workload. So they thought about how to define caches, how to define SMs, how to define their TLBs or whatever is all tensor cores, all defined for that workload. So my optimistic point is that moment we have the adoption with the GPUs with the current breed, and it becomes a prominent workload, as Jensen has publicly mentioned many times, I'm sure the next generation workloads will, GPUs will consider how do we handle the data movement problem, how to make that thing better for data processing workload, right? It is not as designed yet. We are trying to repurpose something animal designed for 2 other workloads into data processing right now and still trying to get value out of it. But moment it become big enough, I'm sure NVIDIA will consider, and maybe they added NVLink for something else. Why not have better PCI or hardware DMA or whatever to do this back and forth movement, right? And so.
But you know, then scale of economies wins, right? Like some of the hardware builders, they can go and buy HBM in really large quantities, so it's cheaper for them, so they can build the card. That's why the second generation or the third generation behind, like the older generation, you can have cost effective, right? If let's say I start a startup today and I want to buy HBM memory, it's going to cost me a lot, right? And then of course the question is, can I do it without HBM? What can I sacrifice, right? That economies of scale help NVIDIA, AMD, and other accelerator builders because they have volume, right?
Right. We are getting the right hardware acceleration as it is because we have, let's say, decompression, which is a quarter of our CPU cycles goes to decompression, and what we hear is a Blackwell generation has at least some decompression in fixed function units, and the Rivas gear will also have something of the sort. So it's already coming. And now the question for us is, okay, if you can move data into the device at 20 gig per second, let's say over PCIe 4, what is the set of operations that you can keep doing on the device at an incoming data rate of 20 gig per second? And okay, so if your in-device data rate is like 100 times that, like 2 terabytes a second, then probably you can do hash join and group by and stuff like that that keeps missing the cache all the time. Because you got to remember these super high throughputs are not random access, they're sequential access or data copy or stuff like that. But it's getting there, and we're really like at the threshold of maturity here. And what about workloads? Well, the AI adjacent ones are interesting, of course, because there we already have the equipment. And now the general purpose stuff we shall see. But it's our belief that we also, inside Meta, we want to promote this idea of using accelerators for general purpose data. But of course, for us, the most readily available is the AI adjacent workloads.
Yeah, I think I would like to touch on a topic that you, Rajan, you mentioned in your presentation, which is benchmarks. I think we keep like seeing benchmarks from different systems that run TPCH, TPCDS, different scale factors, different hardware platforms, different environments. It's really hard to kind of compare and see how they actually compare price-wise. So how could we do a better job? It seems like you guys have been putting a lot of thought on that, right?
So if I may just, one is a distinction between what are we benchmarking, right? Obviously there is a discussion about what the next generation benchmark should be at the TPC-DS level, right? At the end user level. So that's a valid discussion to have, because TPC-DS today does not represent AI workloads or modern workloads. So that it needs to happen. The second point I was making in my presentation is that we need to normalize at the hardware level which hardware is better. Because right now we just had a discussion whether it's a better PCI bandwidth or better HBM bandwidth. All that contributes something to a application performance. And like in CPU world, we used to argue my core has, I think there was a question in the morning to Ori, mine is a 128 byte cache line and yours is 64 byte cache line. This is much better. I have 512 TLB entries, you have 128, this is much, but that's like a cherry picking a feature of a processor to predict the application performance, which is very hard. So that's the same thing I predict that is going to happen in this thing. My GPU is better than yours, or my AMD will say whatever, just to pick some names. In order to avoid that, I think there is a room to define a normalized name, could be whatever, Apple or Orange, but it's a DP mark, which is to say that, okay, if I have a two processor with DP mark 10, that means something from data processing point of view. Maybe both have tensor cores, we don't care, and we don't want to benchmark those. Maybe they have some other hardware, video encoder, decoder, we don't care. We want to only benchmark those processing elements based on what the data processing is relevant out of that, right? So that's what is the meaning of DP mark, so that I'm not even paying for it and I'm not even contributing. Some processor may say that I have a better video encoder, decoder. It's no use to the DP processing, right? I would want to discount that. So hence I believe there's a need for a DP mark to normalize the various heterogeneous computing elements. But the second point is, yes, at application level, I think it's a valid debate to have whether TPC-DS has run its time, because it has so many variables, planner and optimizer and execution engine, which goes into making the, and it also is gap between it and the new applications. So that, I think, has to be a different debate. So that's my
It is always really interesting how many signals come out of query plan differences rather than anything else. We've done a lot of comparisons of the Velox built-in plans versus some internal plans.
Correct.
And that ends up, like how you did the work, how you planned out the work matters more than the execution layer in a lot of cases.
Exactly.
So that's not going to go away, though, sadly, for the application layer. But in the micro benchmarks idea, that does have a, there's no complement that we have there.
I think there are 2 or 3 constituents to this topic. One is the end user, right? They don't care about my microbench, DPMark, or QDF benchmark. They care about what is the performance they're going to get at application level, right? So for them, planner, execution engine, chip, they just care about performance per dollar. So there is and every customer we go to, we spend so much energy putting TPC DS queries and optimizing. We show it to the customer, the guy says, I don't care. Move on, give me the performance on my workload. Nobody actually, zero customer, excuse me for that, but any of the customer we talk to, nobody cares about TPC-DS. They want it because everybody talks about it, and for us as a vendor have to work really hard to optimize it and show it. But when we go to the customer, they say, okay, forget all that, let's get in the door and let's do a POC on our workload, which is the right thing to do because it's not reflective of, I think that gap, if we bridge, between having a synthetic benchmark which reflects a modern workload, lot of ambiguity between vendors and the customer will bridge. So that is much more important as well. But then the subsequent layers of benchmarks are more important for us to builder of the platforms. Okay, are we doing apple-to-apple comparison? So that's my perspective on that.
Yeah, I'm very glad to hear that because, of course, having spent a lot of time on TPC benchmarks and they are extremely sensitive to you having the exactly right answer to the trick questions, and they're built-in trick questions. And I was designing the graph database benchmark LDBC, and we invented particular trick questions to incentivize this kind of optimization over the other kind of optimization. And benchmarks like application-level benchmarks as the TPC ones or the LDBC ones that we were making are just like that. And I don't know, can you entirely get rid of them or should you? Probably not. We think that this feature engineering benchmark that we've been talking about is a step in the right direction, but it's a lot of work and it's a lot of influence games to make it accepted. So it's refreshing to me that Rajan is talking about DPMark, because DPMark would go a long way to standardizing some things and making our implementations more comparable. I mean, everybody claims anything from 5 to 10x. That's fine, but these we cannot do very much with these comparisons unless we have much more context. And so I think this DPMark thing is a step in the right direction and is a lower hanging fruit than redefining the next TPC benchmark for the AI age.
Yeah, I think that this idea is really strong, like normalizing whatever happens on top of the device so we can actually compare different hardware platforms. Yeah, I think that makes a lot of sense. And there's also the discussion of how we can come up with new benchmarks that reflect what people actually do, not what people did 20 years ago.
Exactly.
Which is another good topic in itself.
Right. I think that, just if I want one remark, that requires a discussion with the actually in your case, you are on both sides. You are the user as well as the producer. So you are in a very unique position to reflect what user cares and what we care from this side, right? So, but having a communication with the customers and users, what they care about, where the workloads are moving, and do they care about performance per dollar or performance per watt, whatever the metric, right? So those are important, but I'm glad to hear Ori's comments also on DPMark. Thanks.
Yeah, I think we're in a very privileged position where we have the use cases and we develop the platform, right? So we can kind of co-design them a little closer together, but it's depends on the market you're in. Before we open to questions, I do have I want to touch on at least one more topic, which is this idea of how do we extend those platforms to be actually not generalizable, but to cover a good spectrum of use cases, right? I think there's this idea that having something that can run TPCH, TPC-DS is not easy but doable, right? But having something that can run every single workload with every single UDF and data type that can run everything from Spark, like that's a much longer journey. How do you guys see this idea of how do we complete this long tail and make those engines actually full-featured? And I think maybe Greg, because you've been working with libQDF for
the
a while.
approach that we're taking in QDF with this is to use NVRTC in more places. So use JIT compilation to handle cases that are precompiled rather than trying to you know, we have a few tools to do kind of arbitrary expressions in CUDF. We have an abstract syntax tree part of the library that steps through a tree and then processes it in a kernel per row way, kind of an interpreter kernel. But we've used it for a long time because you can pre-compile it, but it has a lot of downsides as well. So, Velox Wave has shown some pretty good ideas with JIT compilation, and I think that's going to be a big part of the UDF story. In Spark Rapids, they have a lot of they have to solve the UDF problem as well, and for the most part, they have to fall back or break things down to binary ops and CUDF where they can. But there's probably still going to be a role for CPU fallbacks for a long time for some of these particular operators, and doing that efficiently is great. We would love to have like kind of everybody contributes their 10 favorite UDFs into a pool, and we figure out how to accelerate them. I think that'd be a really valuable, without having to get into the certification and specification part. Just like let's throw out some UDFs that are maybe all Java and tricky.
That's kind of what we did with Velox, right? We had kind of the same problem. We started re-implementing some things, moving from Java to C++, and then we have the same thing, right? Like having hash joins and table scans. It's a lot of work, but it's doable. But then you have hundreds and thousands of UDFs to re-implement, and I think that's one of the areas where we got a lot of contributions from the community, and that's one of the reasons why we could move so fast, right? But then questions like we will have to do that again for GPUs and maybe potentially for other types of accelerators. And if there's a magic way to automate those things, that would be great.
Yeah, just to throw in one other thing. When you opened the panel asking about adoption, and my panelists up here started talking about hardware, I really got shifted without a clutch, because I think about that as a software problem for the most part, and making adoption painless and easy and complete and performant on this long tail is, we've got a lot of the hardware. We've got a lot of the bottlenecks in a good place.
It's a software problem, right?
Yeah.
Because of the AI wave, right? So it let us use the hardware. So now I agree, now it's a software problem, right?
Pedro, can I make 2 comments? So one is, actually I want to underline what Ori has mentioned here as well as before, which is that goes back to the question you asked Pedro earlier. What would it take for adoption of accelerated computing to take off? Right, that's the question which is on our mind. We answered earlier from technology point of view, hey, IOs are improving, blah, 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 which is also true. I think there's a practical aspect of it, because we are trying to apply a new widget or a new animal or new step function into a legacy problem, right? Which has a very broad spectrum of functions and operator and something. So I think it is a common goal for all of us to figure out how to bridge that tail function, that long tail that Ori says, as quickly as possible, so that they are all available and we catch up with that broad spectrum. So that's kind of the problem we inherit, because it's a legacy application, legacy function with a broad spectrum. How do we bridge that? So I think that's a community level problem. And the second is, I mentioned in my slides, but I think this notion that we are falling back is true in today's context. But I want to argue that going forward, moment we have enabled 1+1 execution engine, Velox plus GPU, Velox plus FPGA, or SIMD plus whatever, that means I do see a world where you would have domain-specific execution engines coexisting at the same time and being operated on the same job. Right? So you would have a PDF file being processed along with the structured data, where you're doing a join on maybe join is happening on some other engine and PDF extraction is happening somewhere else. So that means the problem is not so much about falling back. The problem is more about how do we do the domain crossing more efficiently? How do we have a common memory format? How do we make the data movement more efficiently? So if you look from that angle, yes, fallbacks need to be solved for sure in today's world, but I think there is a bigger problem to solve so that we can have a more unified platform from structured data, unstructured data, and
I think maybe dispatch is a better word than fallback, because it's going to get more diverse. We were talking, Binwei and I were talking about how Gluten offers many different execution layers. So
right, you're agreeing.
Yeah, I'm agreeing.
Okay.
Yeah, so I think for in particular for GPUs or SIMD platforms, I think there's a possibility. I mean, composability is not entirely a pipe dream, because particularly if your platform is such that it processes arrays and pointers, the ABI agreements can be quite simple. I mean, we just need to, okay, arrow is something. Okay, arrow plus string views, or like Pedro added stuff to arrow the other year. string views and list views. That's pretty much it. If we can standardize on that, and then we can standardize on some policies for variable length data, and then we can standardize on errors, then we can have a pool of reasonably interoperable pieces of SIMD code that we can then JIT, and NVRTC seems to be the way to address this type of platforms. And Revos is also offering a similar capability or even the same capability. So I think there's something to be enabled, to be unlocked in that space, and it's not an extremely high fence before we get there if we have like a desire to do that as a community, because I don't think any of the parties here is like super strong in this particular domain already.
One of the things that I think is missing for making all these things both real and excellent going forward is sharing resources. When you use UDFs, when you use different systems, if you're going to compose a workload across multiple engines but share hardware, right now, I don't know how everyone else here does it, but the most common thing is, oh, I've got these two different things. I'm going to give you 20% of the memory and you 80% of the memory, and then we're going to go off on our way. But accelerators, while they have a lot more memory now, it's still not that much. And you still like have these really spiky consumptions. You know, it's not, you know, memory utilization, if you, even when we saw on Greg's slides earlier, right, the amount of, like, the GPU memory being consumed during the processing time is not constant at all. And so if we're gonna, if we want to like make real UDFs someday and like have things, have these systems actually work together, they need to be able to say, give me a little bit more, give me a little bit less. Like, they need to be able to give that back without having to rely on something like just the driver, right? Which is, you know, you can do CUDA malloc and CUDA free, but if you're trying to write fast CUDA code, you better never use those APIs except for once at the beginning and once at the end, if that's how you're going to do it.
Wait, are you saying that the hardware platform or the kind of the software platform should do that for you, or did the application view?
The applications need to do it. I think that, like, in my dream, there'd be like remote RMM, right? Like the Rapids Memory Manager, which would allow different processes to share resources. And, you know, there's all different kinds of ways that we can talk about doing that, about, like, you know, how you request an amount. Well, you can't always get it, or sometimes you'll have to wait longer. But
yeah, I mean, we did a lot of work in this domain in what Mang presented today in Velox. No, that's not for accelerators, but the problem set is very much the same. How do you manage like multi-tenancy between the conflicting demands? How do you regulate them? How do you police this situation? And that's something derivative of that work could apply in the accelerator space, and that's, I agree, a key part of the interop story or the composability story here. And I think we should all like sit down and see what would be like the critical unlocking factors for us to get this show on the road.
There's been some progress with shared allocators. Like I think PyTorch and TensorFlow both let you define an external allocator, and then if you can have a shared allocator, then you can, you know, the process can work well together. I don't think we can share between processes, but if you can at least handle some kind of pre-processing before training, that's useful. I think in the AI data pre-processing case, though, it's going to need to be kept separate, because you can't ever let the training job. It needs to stay fed, so it can't fight with itself to use memory to feed itself. Like, it's just going to be too risky and unstable. I feel like, to have it on the same node. What is your take on that? How much pre-processing can you put on the trainers?
Well, see, if the trainer has 80 gig or some multiple of that in memory, then it likes to consume batches of 1,000 rows, and if the rows are a megabyte a piece, then it's like 1 gig a batch or something like that. So it consumes stuff a gig at a time. And then if you can produce a gig at a time, consuming, let's say, another gig for intermediate results and staging and decompression and stuff like that, then out of the 80 gig on the A100, you would be using 2 gig for staging and decoding and stuff like that. I think that's an acceptable trade-off. So, and these are very much like fixed width stuff. The hash tables and things like that you have in analytics and ETL are the things that are unpredictable in size, and the group by cardinality, you don't know that ahead of time and stuff like that. And they need to be more adaptive, whereas the AI workloads tend to be like fixed width things that have a pretty set size and even want to process fixed size batches.
Well, this is a much more bullish case than I was expecting. That's pretty exciting.
I think more practically, the sense we got from the trainers team is that they're very busy just making sure that the thing doesn't blow itself up. So I think getting to a point where we can actually share safely, I mean, it will probably happen, but I think it's a year, a couple of years in the future.
I mean, you got to have fixed size allocations there, and you have a trade-off, and there's all kinds of contention there. But it's possible to do because the whole thing is about having fixed size matrices and fixed size this and that and fixed size input batches. So it's a solvable problem. But the less solvable problem is the resource sharing in multi-tenancy query processing, where the needs are less regular and less anticipatable.
I think this is a very good discussion. We probably could stay here the whole day just chatting about this, but we did promise we would open for questions, and I'm sure people are dying to ask you guys questions. So if anyone, just there's a question over there. Please let us know if you're directing the question to someone or if it's open, just open.
Sure, yeah. It's a great conference. Thanks for that. My question is for Rory. Yesterday in the Masha's talk, there was a description of why the AI workloads cannot be expressed in the SQL, and Ori also touched upon that today. Can you just talk a little bit more about it, like how that language may look like? Is it gonna be better API in terms of data frame, or it's gonna be a newer DSL language? It's gonna be imperative, procedural. Like, what's your thoughts on this?
I think I would say, okay, SQL, the VP from IBM said SQL is king, and I like SQL. And if not SQL, then at least declarative, because declarative is what you can optimize, and declarative is what you can make inferences about, and declarative is what you can parallelize. So data frames, of course, you can interpret data frames as an alternate syntax for SQL. So the things that need to be expressed are things like this reversible functions, DS shift, mixing ratios of unions, certain ordering criteria that are not absolute. The mixing ratio I already mentioned, fixed size batches of output, so that if you have variable size batches, then if there's a small batch, the rows have overweight, and if it's too large, they are underweight, and this training is sensitive to that. So these are the sorts of things. I would say many of these could be seen to be flags to a window operator in SQL. Maybe that's where we'll put them. But as we now do have like a language play, we will be looking for ways of expressing these things in a declarative way that you can optimize and you can build a compute around. The solution is not entirely clear. There's also DuckDB has like syntax sugars that are entirely interesting, but do not really speak to this expressivity question. So we'll be blogging about this, and we'll be designing stuff for that. And we hope SQL process is exceedingly long, so I don't think these will make it into any standard in the immediate future, but they will make it into some implementation of ours.
And if I may add, I think in a way the language discussion is even a little less important, right? What you want to do is you want to have the plan and execute that efficiently. Now, if that comes from a SQL statement or a data frame or some other imperative language, you can even provide many of them and kind of for different use cases. I think as long as you can get this plan and you can execute that efficiently, that's I think the thing we care about the most. And with that said, I think all the training things, at least that we have internally, they're all data frame. The discussion is usually that, like, could those things be unified, and could you also support SQL? And I think in general the answer is yes, right? Again, the integration point is usually the plan, not the language itself.
Thanks.
Other questions?
Polars did a pretty good job allowing you to do optimization on a data frame plan with the collect operator, their lazy frame abstraction. Pretty cool.
What is that name?
It's in Polars.
Polars.
My question for Raj, you mentioned that I/O now catch up with communication. This is the reason you created your company?
Sorry, can you repeat?
You said the I/O can catch up now with computing.
Yes.
Or communication catch up with computing. Is that the motivation for you to create your company?
No, that's not the only one. And it's not a futuristic statement that I/O will catch up. I think the point we were making, collectively we were observing that if you know Moore's law, that was for the computing side, for general purpose CPUs, has stopped or has flattened or is dead, whatever people use.
Slow down.
Exactly. So it is not like you're not doubling the performance of general purpose CPUs every 18 to 24 months as it used to happen earlier. So that's one thing, but that has not slowed down for accelerated computing. NVIDIA is a perfect example of that. That has not slowed down for IOs. Your PCI bandwidth, your Ethernet bandwidth, or network bandwidth, and memory bandwidth, those are still improving on that. So if you look at last 5 to 10 years of if you plot the charts of how the Ethernet has improved, the PCI has improved, the memory DDR5 or high HBM has improved, and put the plot with the CPU performance, you will see that those are like rocket ships growing exponentially, but the CPU general purpose computing has slowed down. So that was the point we were making, that I think he was making that there was a gap early on when the GPUs were there and the IO was becoming bottleneck quickly. Now it is not. So that's one point. But if I may want to use this moment to explain why we formed DataPelago, that was more that CPU alone is not enough. We are born into this heterogeneous computing world where you will have a variety of processing elements. And all the existing data platforms were designed a decade back for different world. So in this new world, there is a need for a new thinking, a new platform, which is a function of what we just talked about, right? So that was I hope I answered your question. Yeah.
So the GPU doesn't follow Moore's law? GPUs?
Well, it does not. I mean, if I may want to say that way, because if you look at empirically, it has been improving performance every generation to another generation, so it has not slowed down, right? So if you look at the NVIDIA's I think Greg can speak much more.
You're doing a great job. I don't want to stop you.
Yeah, and I'm happy to say about that. But yes, if you look at the NVIDIA's last 18 to 24, whenever there's a GTC conference, yet another is the new GPU with double the performance, right? So double the cost. But at least performance is definitely doubling or improving, right?
So how did you manage to do that, Greg?
Oh, it was easy. Let me tell you. No, it takes a really long view and a huge talented team and a global team to do it. And yeah, I can't. I'm not qualified to speak to the origins of NVIDIA's success here, but yeah. But it involves a different programming model. It's if you look at the clock speed of the threads in a GPU, that's following Moore's law.
Yeah, I mean, I can answer offline. I don't want to hog this time here, but yeah.
Yeah, I think we only have a few more minutes. Let's take maybe one more question, and then we can wrap up. Deepak.
Happy to take the last question of the conference. So one of the other harder problems I see is also profiling. Like, how do you, so current tools, you have one tool for like CPU, one tool for GPU, and maybe one tool for a specific hard accelerator. But I think like when you combine all these, it's going to be much challenge to understand where the performance is, going. So what do you guys think about that problem? Like, do you think we need a tool that sort of combines all, or a new paradigm?
We at least need one that can cover multiple GPUs and multiple nodes and CPUs simultaneously.
Wow,
it's really hard.
NVTX does that already, no?
It's tough when you have a cluster and you have to manage a lot of data comes out of that. What we need is a hardware accelerator for hardware accelerator profiles.
If you eat your own dog food, you can do it.
I know.
That's the way to do that. But
yeah, I mean, automation of Nsight systems data is a thing that we we're working on in my group and working with the Insight Systems team on a bit as well. They're trying to add more automated tools to work through this to get the thing that you need. Like earlier we showed table scan breakdown of I/O, decompression, and decode. And that's automated, derived from profiles. But that's not part of the mainline thing yet. So there's definitely a gap. And we need to, we haven't solved the multi-node thing, how to manage the
I don't
the
think you can do it
gigabytes.
on the driver. It's too much information. I think that if you really want to do this well, it must be directed by the builders of the engine using things like OpenTelemetry or other tools that capture the metrics that you want at the granularity that you need them.
NVTX is pretty great though. Zoltan has a good point. You can attach data to it now. So
You can, and I do that all the time, but it slows down my process, so I'm not actually getting like my real times.
Yeah,
right?
that's true. That's true.
And it will literally change what your bottleneck is because of that overhead. So now you're not seeing that interesting piece of information. Like I think that, by the way, I love like NSYS, right? I use it all day long. It's a wonderful set of tools.
NSYS is awesome. Yeah.
But for what's being described here, I think that we've got to do some of the work ourselves because the engine builder is the one that knows like what they're trying to track and when they're trying to track it and how much they're willing to pay at every single stage to get that information.
I don't know, Deepak, do you think we should add operator stats in Velox?
And metrics maybe.
Yeah, that
Yeah, sounds good. Let's build that.
We have so many of them. I mean, Wave adds some 10 new runtime stats and all that stuff. And NSYS is great, but it's very localized information. What are you going to do to particularly distributed things like shuffles? How do you measure shuffle performance? How do you measure lost work because of latency of this or skew of that and stuff like that? So these are not GPU-specific things. GPU makes them a little bit trickier because you have still more and more and more of these counters, and there's more counters than you can follow. So you could try a machine learning model to summarize the counters. I've been dreaming, decades long over an expert system that would just say, okay, what's wrong with my program? What's wrong with my query? Why is it slow? And I mean, there's common causes of slowness. It's not impossible to do. And maybe now with better machine learning or stuff like that, we could just train it because, the training works well when you have infinite examples and slow queries are plentiful. So
Yes, that's true. All right, I think that was the last question. Just to wrap up, I just want to finish on a very positive, forward-looking note. So maybe we can go around the panel, and if you guys can just share your view, like in the next, let's say, 3 to 5 years, what's the next breakthrough? Like, what are the things, the kind of interesting things that will happen in this hard acceleration space? And we started with Zoltan, so let's start with Ori and kind of go backwards now.
Okay, so my prediction is that accelerators it doesn't have to be predicted. They're getting to be everywhere. So the challenges that we'll see is that nobody can program that stuff. And the model of programming models and things like that Triton, OpenAI, and people are doing may be good for something, but they're not there yet. So we do need to educate the public. We do need to find some way of multiplying this very scarce pool of talent. And these are some of the minus side. On the plus side is that the gear is there. It's becoming increasingly available. The problems are there. The data is plentiful and is only getting more so. What's going to happen with AI? Is AI going to come to our rescue for generating these programs that nobody understands? Probably not. So will be the thing to see, but it's going to be exciting times, and I think we will see, if not like all around mass adoption, we will see certainly increased validation of our proposition with accelerator-first computing.
Cool. So what are you saying that in 5 years we're going to have AI helping us program those things?
Unlikely. Don't quote me on that. It's a joke.
It's been recorded on YouTube, so in VeloxCon 2030, if anyone is watching, send Ori an email 5 years from now to see if he was right. Greg.
I'm really hopeful about where Velox can go in the next 3 to 5 years as well. There's always a push towards fragmentation in data processing. I don't know if it's getting worse over time or if it's just always really rough and up and down the stack, new experiences coming in. I hope that we can get more unified in the next 3 to 5 years. I hope that Velox can grow and succeed and have more backends available to it. I hope CUDF can be a very powerful backend for anything Velox wants to do on GPUs, and then we can grow up from there. Make sure that the gluten and Presto C++ layers are giving Velox the information it needs to run everything that's coming in from a wide diversity of front end sources and all kinds of applications. I think that it's something we're talking about here, but it's gonna take there's a lot of software that we have to build to pull that off. And but yeah, I think Velox is pushing in the right direction there, and Velox and CUDF share goals, and we're both pushing in the same direction. I think we're gonna do it.
Nice. Yeah, I think that's I think one of the things we discussed for Velox is that, like, if we could get to a place where the sort of execution in data management becomes more of a commodity, like in operating systems, right? You just use Linux. If you want to compile things, you just use C-Lang. If you want to run things, you just run on Velox. Right? So let's see, 5 years from now, let's hope we get there. Thanks, Greg. Rajan?
Yeah, so I think I'm, as I said in my beginning sentence, is that I spent last 15 plus 20 years doing accelerated computing for security, for data movement, for deep packet inspection, and building other stuff. So I don't think there is any escape, and physics is physics, right? So Moore's law has stopped for general purpose computing. So you have to have accelerated computing for this problem as well. There is no escape for that. Data is growing like anything, becoming complicated. Applications are all becoming data-driven. So you have to solve this problem, and I think we will solve it. So I'm very optimistic about it, and it's going to continue that. So that's on the adoption of that. There are challenges, how to debug it, how to profile it, how to have a common memory management. I think those are technical problems, how to have better sorting or better hash or spillover jobs. I think we can solve it together collectively. So that's on one side. Just on a fun side, my prediction will be that maybe the 3 years, 5 years from now, VeloxCon we can have in Vegas. We may need multiple hotels to arrange it. But I wanted to also take this moment to thank Meta team and Velox team to hosting us. It has been a wonderful experience last 2 days. So thank you so much for having this presentation forum.
Yeah, no, thanks for joining. We've been discussing about maybe doing that in China next year. Vegas came up. We also talked about Hawaii. Let's see, maybe. Hawaii. Hawaii would be cool. Can do the beach.
4 votes already here. Yeah.
All right, Felipe.
File formats. My hope. So I don't know if anyone noticed, but up on that screen, when people were showing their workloads, like 60 to 70% of the time is scanning the data. And of that, 2/3 of it was decoding and decompressing. Holy smokes. Like that, we've spent so much time optimizing joins and filters and all this kind of stuff, and then building incredibly complicated file parsers and decoders and decompressors. Like, look at the read parquet. We were talking with some NVIDIA people earlier, and literally, it was mentioned, right? Like, look at the read parquet code. It's quite involved. And I think that hopefully what we're going to see is file formats that have accelerated decoding and decompression built in, vectorizable, where the format itself is meant to be read and processed quickly and not necessarily optimized for how do I compress the most amount of bytes into a thing, or how do I make this easy for humans to understand?
Absolutely. So we did have this file format club for a long time, and this was really the #1 point on our agenda. And we do have Nimble, which is already better in that regard. And we got good work at CWI in Amsterdam that have fast lanes, and these are very GPU friendly. So this is widely acknowledged by the community, and let's talk more about it.
We just need to push Nimble through the finish line, right? We have the right design. And then trust me, I think the pain points of encoding, decoding is something we've been seeing more and more often. I had a whole presentation yesterday about this. So yeah, we can definitely see that. Thanks, Felipe. Zoltan, do you want to wrap it up?
Yeah, I think I would take the other side of that bet with Ori about AI helping us. We're building the systems for AI execution, right? I think in 5 years, maybe we can have that expert system helping us. You just throw there your slow query, you have no idea why it's slow, and build the system that can actually fix itself. I think with the growing compute, I think this might just be possible in the next 5 years. So I'd really like to see that.
Almost like a vibe SQL coding of sorts.
Yeah, vibe SQL coding, exactly. Just explain what you want and let the system build a nice distributed system.
Get your trademark in now.
All right, well, thank you. Thanks, everyone, for joining. I know it's getting already late. Hope that was useful. I'm also hoping you guys are going to stay here at least for a few more minutes. So if you have any other questions, anything else you want to discuss, just come here up front and chat with the specialists. Thanks, everyone, for coming. And Ali, if you want to wrap up.